Okay, welcome. Um, as I said in class today, earlier, the name of this unit that we're in is electrons in atoms. And up to this point, we've been working with trying to understand electromagnetic radiation, and how wavelength and frequency are related, and how we can relate the frequency of electromagnetic radiation to the energy content of that EM radiation. And it's been a little bit computational up till now, and you may well be asking yourself, where are the electrons? That's the name of the unit. When are we going to get to them? Okay, well we're just about there, and I thank you for your patience, because really we have to understand um, a little bit about electromagnetic radiation before we can understand how electrons behave. Okay, so with that in mind, let me just quickly go through some of the key vocabulary. All right, so this is you can pause the video right here to make sure that you have a list of the I think this is most of the key vocabulary that we're going to be going through, at least up to this point. So make sure that you spend some time over the next few days getting familiar with what these terms mean. Okay, these are important. All right, now first, I want to talk a little bit about color perception, our perception of color, because I think that nicely connects, sort of a familiar everyday experience with the concept of atomic absorption and emission. So what we have here, what I'm showing is this rectangular, this little rectangle is represents an object of some sort. So this could be a tabletop, it could be somebody's shirt, it could be a poster, a book, anything. Here, this is simply denoting a source of light, and specifically a source of white light. All right, and here are this represents all the photons of light that are coming from that white light source, and I'm trying to indicate here that all of the different wavelengths of visible light are being generated, are emanating from this light source. All right, and they're striking the object. And this is just like a big eyeball. All right, so that's somebody looking at the object. Um, the way that you the way that we're able to detect and see objects around us is we see those objects through reflected light. All right, so it's impossible to see an object unless there is light, and unless the light is being reflected off of that object. That's what we see. Okay, so if you have an object that happens to reflect all the wavelengths of light from coming from a white light source, like the overhead lights in our classroom, then if all of those wavelengths are returned and are impinging on the retina of your eye, your brain interprets that object as white. Okay, so it's kind of like your brain gets overloaded, and when it's receiving input from all the wavelengths across the spectrum, across the rainbow, it your brain combines all of that together, and that is kind of our concept of white. It looks white to us. Okay. Um, on the other hand, let's say there's another object that reflects all of the wavelengths of the spectrum, the visible spectrum, except for blue light. You see how the blue is missing here in the reflected light? Well, there's something about the molecules in this object that absorb blue light. It enables them to absorb wavelengths of electromagnetic radiation that are in the blue portion of the spectrum. And so when that light gets reflected off of that object, the blue wavelengths are missing. They didn't make it out of the object. Well, guess what? When your eye receives all the wavelengths of the visible spectrum minus the blue light, Do you want to take a guess as to what color you see? Believe it or not, your brain will interpret that object as being yellow in color. So pretty bizarre, huh? All right, let's take another example. Back to white. Here's white. Let's say the object this time reflects all the wavelengths except for yellow. All right, so there's something about the molecules in this object that absorb yellow wavelengths, and so they don't come back off of the object. So when your brain receives all the colors of the visible spectrum minus yellow, do you want to guess what your brain sees? Your brain interprets that object as dark blue. All right, so these are some interesting. Maybe you knew this, but I think for a lot of people this may be a bit of a surprise. That's how your brain works in terms of visual processing. And then finally, let's say that the object absorbs all of these wavelengths of light and doesn't really return anything. Then your brain will interpret that as black. Okay, so when you see something that is truly black, even in a well-lit room, that object is absorbing all of the wavelengths. Okay, and so that's how you see black. All right, now let's think about what happens. How can you tell that there are a whole bunch of wavelengths in that white light? Well, you guys have probably heard of a prism, right? So a prism is just a translucent crystal that that has the property that when light strikes it, when it comes out, it separates the light into its component wavelengths. All right, so white light, as we just talked about, white light contains all of the wavelengths of the visible spectrum, all the way from 400 nanometers, which is violet, down up to, I should say, 700 nanometers, which is red light. And notice that in this illustration, there are no breaks in the color spectrum. It's just a continuous spectrum of colors. And so this is what we would call as I just said, a continuous spectrum. All right. Now let's look at it just slightly differently. Let's say we had some sort of a measurement device that could you shine a light into it, and it can tell you what the intensity is at every wavelength of light between 400 and 700 nanometers. Okay, so we're going to measure the intensity. So let's say we've got there's some light source, and when we analyze the spectral profile of that light, it looks like this. Okay, so you got kind of a big peak right just a little bit above 400 or around 400, and then it's pretty much flatline, from around 450 on up. My question for you is, what color do you think that light would have been if we have kind of a nice peak here around 400 nanometers? Well, hopefully you're getting familiar with your spectrum, and if you have that in front of you, you should have guessed violet, right? Violet or something around that, indigo. Okay, how about over here? Let's say we've got some light that peaks just a little under 700, but it's a little bit broad in here. There's some intensity also in the mid 600s, but let's say the spectral profile looks like this. What color would you predict? Okay, so hopefully you're thinking something in the red family, and it would look something like this. All right, so depending on the characteristics of your monitor at home, this should look like basically red, but it's not pure red. It's got a little bit of an orange overtone in there, and hopefully that makes sense because as you get closer to 600 nanometers, that's getting more orangey. All right, so and also this peak. This intensity peak is a little bit broad. It's not smack on red. It's got some intensity over here closer to the orange. Okay, what about this? Now here's a peak where the intensity or the spectral profile is much broader. So we've got representation, in the red family, and orange and yellow, and even on into green a little bit. So what color would you expect? Okay, well, here we go. It's going to probably look something like this. It's going to look yellowish, and because you've got representation from almost the whole range of the visible spectrum, this thing, it's going to look a little washed out. It's going to start to look kind of whitish, so it's kind of a light yellow. And then finally, here's like the extreme. So let's say you've got a light source where the intensity is basically constant across the entire visible range. Well, hopefully you're thinking it's going to be white, all right? And indeed, it would be something very close to white. Okay, I'm going to skip that for now. Okay, so now we're in a position to understand a little bit better the nature of blackbody radiation. Okay, I know that's kind of a strange term, but I won't go into the origin of the term, but blackbody radiation is something that we can use our understanding of blackbody radiation to measure or estimate the temperature of objects based on their spectral profile. Okay, so I want you to imagine. Well, before I say that, let me just get you oriented here. So this graph should look kind of familiar. We've got wavelength on the horizontal, just like we did back here, right? But instead of being in nanometers, we are in, you see this? Remember what that symbol is? That's micrometers, all right? So this is 3 micrometers, and because 1 micrometer is 1,000 nanometers, this would be 3,000 nanometers. This tick mark would be 2,000. This would be 1,000, and then here we go, 900, 800, 700. Well, what do you know? We're right at the edge of the visible spectrum with red, and we know that 700 nanometers is the high end, the top end of the visible spectrum, and that's where red is. And then down here, this is 400 nanometers, and that's the other end of the visible spectrum where violet is. So I hope that this scale, makes sense. And then you've got intensity again along the Y. Okay, so the way you can think about blackbody radiation, and please, for people who are watching this other than my foreign high school students, this is very basic. This is just like a first pass look at blackbody radiation. So if you want a more, sophisticated treatment, please, go to Wikipedia and look up some references there. This is for high school students. All right. What we need to know is, or what you need to think about is, we've all seen an object that is really hot, like the burner on a stove. When you turn an electric stove up to really hot, you know that the filament glows kind of a reddish color, right? Because it's when it gets really hot. And so blackbody radiation is it's kind of a, well, let's just talk about the intensity curve here. So at a very high temperature, a temperature that is about the temperature of the surface of the sun, all right, maybe around 5,700 degrees Kelvin, that you have radiation coming off of that object that is with a broad range of wavelengths. Okay, and so you can see that you've got intensity between the 1,000 and 2,000 nanometer range. Okay, and that's the infrared region. So obviously there's a lot of heat here, and then you also have a lot of intensity right in the visible part of the spectrum, and you can see that every wavelength across the visible portion of the spectrum is well represented, and so you should expect that the light would appear, kind of white to our eyes. And that's what this little symbol, it looks like a sun, and this is from, I should say, that this screenshot is from a FET simulation. So we've done a FET simulation before with radio waves, and this is the blackbody radiation simulation from that same website. And so what you can do is if you go to the simulation, and I encourage you to play with it, when you scroll the temperature up and down, you'll see how the spectral profile changes. Okay, so as you go from high temperatures to lower temperatures, the peak of the spectral profile will shift to higher and higher wavelengths. Okay, and the color of this little sun icon will change, and it'll show you what the object at that temperature would look like. All right, so let's start at a lower temperature. Let's start at 1,000 degrees and then work our way up. Okay, well, you can see that, there's very little intensity, no intensity in the visible part of the spectrum. And if you look really closely, you've got a little bit of intensity out in this range, and this is the infrared. Okay, so there's heat coming off of it, obviously, if you're 1,000 degrees, and the color would be just a dull red. Okay, so it's getting hot enough that the object is just beginning to show a little bit of red. Okay, now let's make the temperature go up. So we put the temperature up 2,000. Now you can see that there is really appreciable intensity in the IR. And down here you can see that we're getting to have a little bit of intensity in the red and orange part of the spectrum, the visible spectrum. And you can see that the object would indeed start to be glowing kind of a reddish orange. Okay, if we take it a step further, let's go to 3,000 degrees. Now, let me step back. Okay, the peak of this thing was like between 1,000 and 2,000 nanometers at 2,000 degrees. At 3,000 degrees, the peak of this intensity curve has now shifted to about 1,000 nanometers. Okay, it's shifted to shorter wavelength, and so we're getting a lot more intensity in the visible region, and you can see now we have a nice orange color. Okay, and then if we go even higher, 4,000 degrees, now the peak is below 1,000 nanometers, and it's starting to look more yellowish. And if we go to 5,000 degrees, the peak is now like right in the middle of the visible spectrum. You've got lots of intensity all the way across the visible, and now it's starting to look white, isn't it? And if we keep going, now you can see the peak is getting into the blue part. And yeah, when things get really hot, they go from white to kind of taking on a bit of a bluish tint. All right, so that's kind of interesting. So I just want to, I want you to have a little bit of a feel for the intensity curve here with respect to wavelength and temperature. Interesting stuff. If you want to know what our sun is like, well, so here's wavelength on the X back into nanometers. You can see between these two dashed lines, this is the visible part of the spectrum, and the yellow profile is the intensity curve for sunlight that would be received above the atmosphere of the Earth. So, before it goes through the atmosphere, this is the intensity curve. The red profile is the intensity curve at sea level after the sunlight has filtered through the atmosphere. Okay. Okay, so listen, I'm going to break this into two parts. And so that's the end of, this is kind of like setting things up for atomic emission and absorption. So I'm going to break here, and I'll see you at the next video.